All right, good afternoon, everyone. It's my great pleasure to be here at Riken, and it has always been a joy to be in Japan, actually. So yeah, as Takayuki mentioned, I'm Hao. I'm from University of Massachusetts, Amherst. And I'm in the College of Information and Computer Sciences, and I'm also directing the Human Centered Robotics Lab at UMass Amherst. And for today's talk, I'm going to discuss our recent research on this topic, the lifelong collective autonomy. All right, so great. So over the past many years, there has been always a long dream and a desire that we wanted to improve human existence through the seamless integration of AI-powered robots into our society and industry. And the general goal is to improve, for example, independent living, improve like safety and productivity in not only our society, but also in the industries. So the images I've assembled here shows some of the most promising visions in robotics today. And here you can see it actually ranges from many different applications, from connected driving, connected autonomous driving, from homeland defense, space exploration, to manufacturing and construction. So, for example, like over the pandemic time, we see a huge increase in the costs and in the cost of human labors. And generally, people started to think robotics as a promising solution to address these shortcomings. So when you look at these images more closely, you probably have already noticed several key fundamental capabilities for robots. And robots are cool, and robotics is also promising. But to enable robots to achieve all these applications is actually pretty challenging, okay? And to enable our vision of these AI-powered robots, especially if we want to deploy them into the real world, we generally need to address three fundamental capabilities. So the first one is time goes into infinity. So that's the lifelong autonomy. And as you can see from this video, we have an autonomous vehicle driving in the same environment across 4 different seasons. And you can see that the environment actually changes dramatically over time, right? Like in different seasons. So in this situation, we generally expect robots to not only perceive the environment consistently, but also behave or act consistently in all these 4 different seasons. So this is essentially the idea of lifelong autonomy. So also, robots, especially like multi-robot systems and the human robot teams, they actually provide a more natural solution to address larger scale applications. For example, homeland defense or search and rescue. And in these situations, we generally need the robots to coordinate and collaborate with each other, and also be able to team up with humans to solve more complicated problems. So essentially, we need the capability of this multi-robot coordination and collaboration, maybe also with humans in the loop. So when we deploy robots into the real world, this robustness and resilience is really a key factor. This is definitely a fundamental capabilities for robots. So for example, if you consider these mobile robots, ground vehicles like running over different terrains in other environments, so the robots generally need to address this unstructured terrain with different obstacles and different terrain characteristics, like different vegetations. And the robots also need to address different atmospheric conditions like rain, snow, and also some of the weather conditions like dust, all these kind of varying conditions. And also, like when robots operate in environments for a longer period of time, robots generally will have wear and tear, right? So they may fail. Their sensors may fail. Their mechanical systems may fail. And over time, because of the degrading performance of all these physical components, the robot performance also will decrease. So in all these situations, generally we want the robots to be robust to all these different kind of changes. All right, and these changes will eventually lead to some failure, and failures are okay in robotics, just similar to our other systems, right? But when failure happens, we generally expect the robots or robot teams to be able to recover back from the failure to a certain level of normal operating conditions. So that generally means the robot team need to be also resilient. All right. So those are the 3 fundamental capabilities that we are trying to enable in my research group. And basically putting all this together, this generally converges to the theme that I want to discuss today, that is lifelong collective autonomy. All right. So this topic, generally, this theme, we actually focus on 2 different tracks that are interdependent. So the first one is lifelong autonomy. So that answers the question like how robots can operate across long periods of time, for example, across days, seasons, and eventually over the robot's lifetime. And then when we expand this lifelong autonomy for a single robot to these multi-robot systems, then we also investigate this collaborative robotics. And that generally studies how robots can adaptively collaborate with others and team up with humans to solve larger scale problems. Okay. So we generally solve this lifelong collaborative autonomy through from the perspective of robot adaptation. And that will be the main topic for the primary topic for my presentation today. So we have been working on lifelong autonomy for almost 10 years, and we have learned a lot from failures. And basically, the next section, like a couple of slides, I'll focus on the lessons, different methods that we developed over the past almost 10 years, and the lessons that we learned from our research experience. So we actually address lifelong autonomy from both in both the perception space and also the action space. And we'll start our first work, that is long-term representation learning. So the problem domain that we focus on for this type of work is generally on like robot navigation. All right, and the first problem we are trying to solve here is the visual navigation in these open worlds. And the goal is for a robot to orient itself in the physical space and then navigate from point A to point B using like visual observations only. And because the environment actually, we try to enable this lifelong autonomy. We generally, the first thing we want to do is to create a long-term representation of the open world. And it's actually not that easy, okay? And there are two primary challenges that we need to address. So the first one is called the perceptual aliasing. And the definition is, different places may have similar appearance. So as an example, like the 7-Eleven here, they all look very similar. If robots rely on these grocery stores as landmarks to localize itself and to navigate, then they may have a problem. Okay, so this is the perceptual aliasing. And the other challenge is on the other extreme, that is the long-term like changes. So generally it means, for a long period of time, the environment may have some strong appearance changes and structure changes as well. And that may happen, for example, across different times of the day, across different seasons. And for example, going back to this 7-Eleven example, the stores may just change their stickers. They may look quite differently in the next month. Okay, so this is the so-called long-term changes. And our first work is to implement some insights to create this long-term representation by implementing this in the idea of this inherent location sparsity. And the meaning of this is it's generally infeasible for a robot to simultaneously exist at two different places. So robots cannot teleport. So that's the idea. And we generally provide some mathematical framework to model these insights. And at the same time, within the same mathematical framework, we also implement two other ideas from the simultaneous localization and the mapping or SLAM communities. So one is based on this sequence-based representation. So basically, we want the robots to have some active perception capabilities to just look around, collect more information from different perspectives in order to reduce this perceptual aliasing. And then they also implement the idea of this multimodal sensing that actually create a diverse descriptions of the environment that can help actually to address these long-term changes. For example, the appearance of the object may change, but the structure of the object may not change. So this is kind of the idea we are trying to encode. So based on that RSS paper, we further combined this long-term representation to estimate the robot states and then integrated with some navigational control under the Markov decision process. And the goal here is to achieve this called the mapless navigation. And the approach name here is called the sequence-based multimodal appearance learning, or like a small. So for this mapless navigation, this is an example. We generally show the robots a few demonstrations for the robot to explore the environments. And we wanted the robots to follow the same trajectory under the changes of the environment. So that's the goal. And we sort of quite quickly evaluate that in the simulated environments and also this relatively simple mockups in the indoor environments. And then later we actually deployed this approach on real robots working in outdoor environments. And the environments really shows some obvious changes for different times of the day, they have different illumination conditions. And also over seasons, the trees may become greener with leaves or without leaves. And our approach is able to address the problem pretty well. And it relies on multimodal sensors, right? So in this example, use LiDAR and camera. And from camera, we actually extract the different these efficient features that actually captures different aspects of the environment. Okay, so that's the small approach. All right, so basically this small method creates some general representations that can actually robustly encode some small variations of the environment. But apparently it has many limitations. So first of all, when we consider about the off-road robot navigation, then the terrain characteristics actually affect the robot navigation performance a lot. And the previous method actually cannot actually encode this kind of terrain characteristics. And also, in the real world, we see this dramatic sudden changes of the terrain types, and that is also not modeled in our small approach. Okay, so to address all these challenges that I just mentioned, we actually started another track of research. It's called adaptation to changing environments, and we developed two different type of methods to solve this problem. And the first solution is to adapting model parameters according to the context. And the approach is called TRAIL, so Terrain Representation and Apprenticeship Learning. So that's also published at RSS. And the definition here is we want to define the parameters of a navigation policy as a function of terrain type distributions. Okay, and this terrain type distributions is generally considered as the context. And without going into math details, on above the equation, it generally shows the meanings of these equations. So basically, we have this, it's based on regularized optimization. So basically, we have a loss function to learn the representations of the terrain, to learn the distribution of terrain types. And then we also have another loss that is apprenticeship learning or imitation learning loss that actually try to learn, from human demonstrators based on the current context. And we have this, sparsity state regularization terms that is, for example, to encode our location sparsity ideas. And basically, this approach enables a ground robot to adapt its navigation in real time to a wide variety of terrains in the field. So these are some demo videos that the roboticists always like to use. So here you can see at the bottom left, actually, that's my student setting up the environment. He actually spent a lot of time setting up the environment and clean the robots. And then we generally on the top left, that's the standard learning from demonstration methods or imitation learning methods. And the top right, that's the small methods that we developed. And then on the bottom right, that's actually our TRAIL methods. All right, so our approach was better than previous methods. So TRAIL implements the idea that we adapt the parameters of a single control policy, policy for navigation according to the recognized terrain type distributions or the context. But we learned actually several lessons as well. So TRAIL has some additional limitations. So for example, this TRAIL cannot really address these highly dynamic and deformable terrains that actually are very common for field environments, like you consider tall grass. And what is even trickier is there might be some hard, static objects like these stones that are hidden beneath the tall grass, or it can be muddy, beneath the tall grass. And previous methods, including TRAIL, generally cannot address those. And the other thing is, there's generally no single policy that actually can address this whole diversity and meet all the navigation criteria. All right. So one obvious example is, if we consider this obstacle avoidance policy like a matrix with this, navigating over tall grasses, they generally compete with each other, and it's generally not that intuitive to actually implement the both criteria together. Okay, and then to address this problem, we come up with a second idea that is called the negotiation for adaptation to unstructured terrain surfaces, or NOTS. And for this idea, our assumption is we have many different primitive policies that are designed or learned for specific situations. And basically what we are doing is we on the fly, we actually implement a negotiation criteria that actually allows these different policies to negotiate with each other, and altogether they actually can come up they can become like a combined policy to generate a specific solution for the current context. So that's the idea. And basically, this approach, this NOTS approach, continuously forms these agreements between these multi-criteria policies and combine them together to address these highly dynamic like terrain surfaces. Okay. So for this specific work, we generally evaluate in this tall grass situations in outdoor environments, and there are like hidden obstacles beneath the tall grass that we do not know as a predator. Okay. So here generally shows the results. So the MPPI is the model predictive planning and control methods, and the TRIO is the method from our previous work, and the Badger is a learning-based approach from like UC Berkeley, from the Bear Lab, and the NOTS is ours. So basically here we generally want the robot to go across the tall grass, and through the interaction with the tall grass on the fly, they actually can combine the different pre-learned policies to address these tall grass environments. And from the results here, basically you can see our approach works much better than the others. The Badger approach, the green ones, the red ones, it also works fine. It generally find a very short cut, like around the tall grass instead of taking a bigger detour. And we further evaluated this in the forest environment and something like this. And the robot generally, in all these experiments, the robots are given like a goal position, and the robot try to explore the environment and find their path through that. There are actually several different trails that can lead from the calibrated position to the goal position, and the robot tries to find them and evaluate which is better. So the results here you can see like NOTS also still performs good. So the right one is still like Badger. You see like these two trajectories are generally have a similar length. Okay, so they work pretty similar and performs much better than the other like baseline methods. All right, so moving on. So for this track of research, we generally developed two methods for adapting like robot navigation according to different terrain environments. But we still identify many limitations. These are generally two major limitations that are identified. For example, like even we have a perfect navigation policy, a single policy or a combined policy, that policy even that can perform perfectly during the planning phase. The problem is that policy generally cannot be executed as is during the execution phase. Okay, and the second issue is all the previous works that I just discussed, they only think about the external context, like from the environment. But we know like robots' capabilities and functionalities may also change dramatically, for example, during the navigation. And then the question is, how can we address these two limitations? So that generally leads to our next track of research that's called the self-reflective adaptation. So for this track of research, we still try to address the problem of mobile ground navigation in field environments, and we generally consider this a maneuver, try to further address this maneuver inconsistency problem. So the goal generally is we want to ensure the robot actual maneuver navigation behaviors match the expected controls while traversing these complex terrains. And it cannot do that because the robot have these so-called setbacks. So these setbacks are defined as changes negatively affecting the robot's functionalities. And for example, if we add some heavy payload, we add 20 pounds at the back of the robot, for example, or we reduce tractions, like we put the duct tape around the robot wheels. So the robot behavior will actually change dramatically. And we also see failures in sensors and mechanical systems as well. So all of these are considered as setbacks that actually add one more layer of complexity to this robot navigation problems on top of this complexity from the environment. All right, so we further developed the two different ideas that are similar, well, that are actually connected. And the first idea is we developed a self-supervised learning approach that actually can self-learn offsite control to compensate for the inconsistency between the plans and also the actual behaviors. So basically, this difference you can consider that as a residual, right? And we are trying to minimize the residual on the fly to make sure that the actual behaviors can perform at can be as similar as the planned behaviors. So that's the idea. Okay. And then the second idea is published in like IJR last year. So generally this one, we develop methods that explicitly enables this self-reflection. So basically we want the robots to be able to monitor its own performance and then try to use this its own performance, the monitoring of its own performance to modulate or like adapt its adaptation processes. And for example, this robot can just monitor its performance changes according, for example, by changing this varying payload or like by changing the center of mass and by changing the tractions. So the robot is able to like monitor that and use that monitoring to adapt its navigation behaviors. All right, so we use several evaluation metrics to measure to evaluate the performance. Like we have this failure rate, the inconsistency, that is the error between the expected actual behaviors and the directness. And we evaluate in different scenarios. So the first scenario is the mixed terrain one that I showed in the previous work. And basically in this scenario, all the approaches work equally well. And because there is not a very challenging environment and the robot, the functionality, even if we change robot functionalities, they still perform okay. And the two most challenging scenarios is this grass to big rock environment and also the forest environment. So the key challenges from this grass to rock environment is we can see the sudden changes of the robot, like the terrain types, and we can also see the very challenging terrain features in this rock environment. So that actually causes a lot of failures. And in forest environment, most of the failures come from this like a slippery and steep slope. And it's also hard for the robot to detect all these small branches when navigating in the environment. That actually cannot be addressed by this approach. So that's why we see there are so many like failures there. But when you just look at the overall performance, our approach still outperforms the previous methods with some significant margin. All right, so then we further evaluate the situations that we change the functionalities of the robots. In this situation, we just wrap the robot wheels with duct tape. So it reduces the traction of the robot. And we ask the robot to climb this actually pretty steep slope that is covered by, it's a grass surface covered by snow. And basically our approach actually enables the robots to perform better. And what is interesting, actually, the robot learns to speed up before going up to that hill. So that actually allows the robot to reach to the top. So similar things happens, in the video shown on the top. And the bottom, we further add the 20 pounds payload to the back of the robots, and we tested in this general field environments. And basically the robot are more easily to tilt over when we add this payload to the back of the robot. And so the robot actually can monitor its behavior changes and try to reason about why, and then try to adapt to that changes. Okay. All right, so recently we actually deployed, all the previous methods actually based on the mathematical foundations of regularized optimization. And then recently we actually, students started developing this deep learning based methods to implement the similar ideas for this robot self-reflective learning or introspective learning. So basically here we add payloads to this, like a small robot dog. And when we add payloads, actually the controller breaks. So it actually cannot handle that payload. And for example, compensating for the changes and by combining different primitive actions, it actually allows the robots to like move smoothly after adding this unexpected changes. Okay. All right. I'll very quickly discuss our more recent approach on this perceptual adaptation to degraded situations. So what interests us is in many of our experiments, we generally see sudden failures of the robots, and we spend some time to understand why that happened. And it turns out because of this. So because when we navigate robot, for example, climbing that muddy hill, mud can partially cover the RGB camera. And when they navigate in the forest, actually the branches generally can cover the LiDAR as well. And basically all the methods assume the perception data are perfect, but that's actually not true in this lifelong autonomy, right? And what is tricky is the robot sensors, they do not fail, but just a part of that sensor is covered. All right, so just partially the data is partially corrupted. Yeah, and the question is how can we solve that? So this is really our recent research. The idea here is we actually use multimodal sensors like from LiDAR, from camera, from other sensors to create a diverse set of representations, and each representations they should be equally efficient if all the sensors work correctly. But if some sensors are like failed, then generally some of the representations actually is much less efficient than the others, and we can use this way to detect whether the productivity or like the representativeness of each of the sensors, and then we merge all the sensor data together. That's how we merge the sensor data together. All right. So if some sensor does not work well, we have this additional sensor fusion methods try to merge different sensors according to the sensor's performance. And for example, in this situation, when the robots, well, when we turn off the lights, when we turn on the lights, the RGB camera actually works fine. And when we turn off the lights, actually the depth camera works okay. All right. And this change can be sudden. This change can be gradual when the robot, for example, like walking through this street lights. Okay. All right. So that's the first part of this talk. So that's on the lifelong autonomy and the lessons. You can see a sequence of approaches that we develop, and we generally address many of the limitations there. And then I'll expand this lifelong autonomy to these multi-robot systems and human-robot teaming. And basically, we'll still focus on robot adaptation, but in the context of multi-robot systems. And the first, I want to quickly go through this so-called collaborative scheduling. And so in this real world, so robot teams, they actually they face complex changes in the task, in the environment, and also in the robot themselves. Okay, so now the good news is we have multiple systems, we have multiple robots. So if one robot fails, then other robots can actually cover that robot. Okay, so that's sort of the idea. And basically, there are like two fundamental capabilities we want to enable. So we generally want the robot to ask what are the capabilities of their teammates. So the robot need to have a group introspection. So the robot knows each other's capabilities. And second is we generally want the robots to be able to find alternatives if some of the teammates fail. All right. And in this situation, we hope the robot teams can adapt together. Okay. So we developed this so-called learning for voluntary waiting and subteaming. And so the idea here is, you see some of the tasks are just too big for each individual robot to solve. And in these situations, we generally want to have a sub-team of robots to take care of that task. It can be, for example, two robots with a smaller payload to carry a big payload together. It can be, okay, now we have a mobile manipulator that actually can perform the tasks for a sub-team that contains a mobile robot and independent manipulator. So those are the alternatives that we can have. All right, and the robot actually need to reason about the capabilities that all the teammates have and try to find the combinations of the capabilities in order to form a sub-team that can achieve certain tasks. So that's the goal. So just to quickly talk about the general ideas. So pretty much all the research on multi-robot systems in my group will focus on graph learning. And this generally shows you an example. So in this situation, we use a graph to represent both the robot teams and also the tasks. So robots on the top of graph, robots are modeled as nodes in the graph, and edges generally are used to represent their representations, their relationships. Their relationships can also be multimodal. It can be their physical distance. It also can be like the internet, their network connectivity. All right. So that's an undirected graph, and we use a direct graph to show. This is a standard task graph to show the tasks and different task dependencies. So that's the bottom one. And then we mathematically formulate as a bipartite graph matching problem between the robot graph and also the task graphs. So then, the bipartite, we solve this bipartite matching problem using like deep graph learning. So what we do is we have a graph attention transformer network that actually integrates the graph attention networks to encode these local graph structures from the robots, from individual robots, individual tasks. And also we have a transformers to encode the global context information. And then after we have all these embeddings from the nodes, from different nodes from the global transformers, what we do is we compute them all together and combine them into this reward function that is used to perform this bipartite matching. So to enable this dynamic subteaming, what we do is we actually relax this classic requirements in this bipartite graph matching. So that is one-to-one correspondence. And in this scenario, we allows like a multiple to one assignments or correspondence. So that generally allow us to assign multiple robots with the required capabilities together as a team to solve a certain task, okay? And to avoid some of the local optimality issues, so what we do is we also enable this voluntary waiting so that the robot may wait for a certain, without performing a certain task that is available at this moment, but wait for the future bigger task that may give us a bigger reward. So that's the idea. And the way we do it, we just add one more task that is like a dummy task that does nothing, just for the robot to wait there. So we add this into this into this matrix and then perform bipartite graph matching there. Okay. All right, so it's still like a imitation-based approach, and this shows a relatively simple example in gazebo environment. And here you can see somewhere, well, right now the robot is voluntarily waiting, it does nothing, even some of the tasks are available. And here you can see some of the robots, they actually collaborate with each other to take care of some bigger tasks here, like a bigger payload. So that's the initial results. And because manipulation is not that easy, so we use humans to replace those many, like robot arms. And we do some similar things on these real robots, okay? And then our goal eventually is to actually move this whole system to the field environments, okay? Consider about search and rescue, right? So right now indoors, if we rely on this external tracking system, the problem is not that challenging. Well, it's still challenging, but we have this roadside infrastructures. But when we move it to the outdoor environments, we don't have that. So we actually have a group of students working on this, this heterogeneous, for example, robots. Heterogeneous robots take carrying some payload, and we have this mobile manipulators to actually manipulate the objects in the field. Okay. All right. So moving forward, for this tightly coupled coordination, so that's another problem we are very interested in my research group. So basically, in this situation, so robot teammates, they depend on each other to collaboratively manipulate and move object that object actually connect the robot together. Okay, so these robots, they no longer independent, and the one movement of one robot will directly affect the other robot, because these two robots are connected by a rigid, in this situation, like a rigid payload. All right. So to solve this multi-robot systems, generally our approach is through this bilevel learning. Okay, so this bilevel learning, it's a part of the hierarchical learning, but we use this bilevel learning mainly to model the different structure of the organizational structure of the robot team at the higher level, and at the lower level, we actually have a decentralized control system to control each robot to achieve this like their own tasks that is planned by the higher level. Okay. And in this specific situation, so the robot coordination actually is performed at the upper level, and that determines the team behaviors. And in this situation, at the upper level, we want the team to satisfy these kinematic constraints, because that constraint is the constraint caused by the payload that actually connect both robots physically. All right. And the lower level, for this one, we actually use this. This one is the reinforcement learning method at the lower level that actually can generate this individual robot actions that can satisfy this heterogeneous or anisotropic velocities. So these are the robot dogs. Robot dogs has different speed limit in different directions, and that limitations must be considered during the planning phase. So that's the idea. And also, this obstacle avoidance, that's always like a functionality that they want to enable. Okay. And the good thing for this is, during the training, it's a centralized training, decentralized execution. So after the training phase, actually these policies can be deployed in a decentralized fashion on the robots. Okay. So these are the results showing from this work. And the scenario that we try to argue about is in manufacturing or these warehouse environments. You have a team of robots that actually just sorting things out, right? And they may navigate into these very narrow corridors between, for example, these the shelves. And then the robot teams must be able to know how to navigate through this narrow corridors. Okay. All right. So the last part of work on this collaborative autonomy from the adaptation perspective is this adaptive coordinated navigation. And the problem definition is, we have a team of robots navigating through a complex environments in other environments, for example, and they must actually coordinate in a certain fashion, for example, to maintain certain information control, right? So if you consider about the search and rescue, those rescuers, they actually have a line formation, right? And you consider like birds, they have this so-called wedge or the pizza formation, right? So the robots also want to follow similar position, like formations for certain tasks. But the problem is, for example, consider this image. When the robot, for example, goes through this, narrow bridge, and it's generally not possible for the whole team to maintain the original formation. And in this situation, how can we adapt the formation? We adapt the shape of the formation, but at the same time still maintain the same formation type. So that's the problem we are trying to solve. And we still use this bi-level learning paradigm. And in this situation, at the upper level, it combines both the situation awareness. So for the robot team together to perceive the width of the corridor, and also to maintain the formation control. And at the lower level, we use RL to train the individual robot navigations, for example, for obstacle avoidance and for like waypoint following. Okay. So these are some of the results. So the first one on the top left, so that's the robot, a team of 5 robots navigating through like a narrow bridge on top of a river in the simulation. And in the middle, we have 5 robots forming a circle formation to go through also like a narrow corridor. And last one is a line formation. Okay. And this work is from last year. So at that time, I actually deployed these robots on these Triton robots that we designed in the lab. And now we have actually some other additional like experiments that actually with more robots there. Yeah, that is submitted to ICRA this year. Cool. All right, so for this adaptive coordinated navigation, we actually did some like many different works on different aspects. So for example, previously we did work for subteaming, but not in this collective scheduling context, but in this navigation context. And the goal is for the robot teams to split into sub-teams, and each of the sub-teams actually goes to cover or goes to certain goal position, okay? And we develop this sort of, we have our ISS paper talk about the theoretical aspects of the work, and later we did some real-world experiments for the robot teams to explore, to collaboratively explore like abandoned mine, okay? All right, so that generally covers all the topics that I'd like to discuss for today. And then the question is, okay, now after 10 years of research on this lifelong collective autonomy, what we have learned and what's next? All right. So the first, for my vision, like my vision for the future work. So the first one is the full lifelong cycle and also the autonomy stack. So, robot learning now is very popular, and but robot learning is not completely equal to lifelong autonomy. Okay, so even you have the term lifelong learning, it actually does not equal to lifelong autonomy. So lifelong autonomy is a bigger theme than lifelong learning. Okay, for example, we also have this long horizon planning from the planning communities that also do similar things. Okay, so from HRI, like human robot interaction, we have this longitude studies also do this lifelong evaluations of robotic systems. And then, my work generally focuses on this on the fly, like adaptation in robotic systems and multi-robot systems. And then we have this classic cognitive architectures that considers memory, for example, that also try to address this lifelong learning, just like our lifelong adaptation, just like our kids. Okay. And then the question is, how can we merge all these contexts, all these different approaches from different domains together to eventually have a full system and can implement that to implement that as autonomy stack that can really enables lifelong autonomy. So actually, for now, we are actually very far away from a real lifelong autonomy. For example, we consider like Roomba, right? We still turn it on, it runs for 2 hours, we turn it off, okay? And the self-driving car, similarly, although, it's sort of like continuous driving, but there's a bridge, there's like a gap between different execution phases, okay? All right, and then the other question is, for now, there's a big disconnection between the hardware systems and the software systems in robotics. And, as a computer scientist, and the robotics myself. So basically what we are doing is, we are given some robot hardware and we deploy and we develop and deploy software systems on those hardware, right? And the question is, how can we do this co-design that can really, integrate the hardware and the software together? So, for example, can we define some hardware actually can support learning better, okay? And whether like we have a car, right? And now we have soft robots. So whether this learning methods or this AI methods can also help the, the design of the mechanical systems. And, when we have this co-design, we have this co-design of the learning systems and also the hardware systems. And during the execution phase, can we adapt them together? All right, so that's another question that I'm interested in. And the last one is, my lab is called Human-Centered Robotics Lab, but I actually did not discuss about any human aspects in this talk. Involving humans in multi-robot systems in this lifelong autonomy is always challenging, okay? So that's pretty much concludes, the last one is we are in the era of generative AI, right? And then the question is, how far are we from using this generative AI to facilitate this action space of robotics, especially for multi-robot systems and human-robot teaming? We see a big, push and a lot of promises for generative AI on, for reasoning, for vision, right? And now, how can we deploy this generative AI for action spaces? That's actually a question that we want to study. Okay. Oh, all right. So without further ado, that's all about my talk. And thank you very much. I'm right on time.
Are there any questions from audience? Okay, thank you for a great talk. And I have two questions. The first one is about the autonomy. That do we have the online interaction, or if you just learn from the offline demonstrations of your robots?
Well, that's a good question. So for this lifelong autonomy, it's actually not that easy to deploy continuous learning or online learning. There are two big reasons. One is they are not fast enough to adapt. You consider like robot adaptation, right? You consider about, you have a UAV flying within a very dark tunnel and to suddenly to like bright areas outside of the tunnel. It actually cannot learn to adapt. It's just too slow. Yeah. And the second issue is it's actually very hard, given that the limited amount of data within a limited time, it's very hard for continuous learning or online learning methods to converge. Yeah. And if you consider the robot, for example, moving between two type of terrains like grass, then go back to concrete and just jump back and forth, it actually never converges. We actually did that type of tests. Yeah. So rarely, if we consider like a small time period, we do not use continual learning or online learning. So the way we do it, I think a promising way to do it is we have to have different primitives like atomic actions that are learned in different situations. And those atomic primitives, they are pre-learned and they do not adapt. There are no continual learning on these policies. But on the fly, we actually can learn a way on the fly, to combine them together. So that actually maintains the stability because of this pre-learned primitives. And at the same time, it enables adaptability. Yeah.
See, thank you. So another question is about the heterogeneous robots. Do you train unique policy for each robot, or you train the same policy to control each of them?
That's also a good question. Well, we actually did both. So I think the general conclusion is it's not that easy to train a unified policy to cover all the heterogeneous robots. That's generally not that feasible in the real world. If it's feasible, I mean, it's that this general policy may not work very well for all type of specific robots. And basically, what we do is we actually design a specific learning methods that are general, like math-based, for example. But it's a conditional model. It's conditioned on the robot functionalities or capabilities. So it can be a same policy, but it's trained separately for different type of robots. Yeah.
So sorry, I have one more question.
Yeah, go ahead.
I saw your demonstrations that two robots can hold one box. Yeah, that's very interesting. Do you train it by? Do they learn it by themselves? I mean, this kind of skill, or do you have some pre-knowledges?
At this moment, we assume we have some like prior knowledge. Yeah, so it's generally a combination of imitation learning and the self-supervised learning. And because the search space is just too big, we can, like, reinforcement learning is actually very hard to converge in this situation. And for this reason, we generally have some initial data set using imitation learning. And recently we have this diffusion-based methods. So that's essentially like learning from demonstration. And after that, we have these self-supervised learning methods to fine-tune the policies, because, you know, for this multi-robot collaborations, human demonstrations are actually usually not optimal. Yeah, so that's why we have this self-supervised learning phase to fine-tune the policies learned from demonstrations. Yeah.
I see. Thank you.
Yeah, sure.
Any other questions?
Okay, thanks for your talk. So in the first part of your presentation, you talked about like representation learning. Could you give some more details about like the methods that you use there? For instance, you are learning both this V and U matrix and
yeah.
So
So let me go back a bit more. So the mathematical framework, you see, like, the paper is from 10 years ago. All right. At that time, deep learning is not that popular. Well, even deep learning is popular. We actually see like all the research we are doing are fully embodied. And 10 years ago, there's nothing can run those deep learning models on real robots. Yeah, outdoors. So basically, this mathematical framework is very far. Oh, it's here. So the mathematical framework here, that's so-called regularized optimization. So the bottom right, you can show the figure. So this X is the multimodal features. And the first loss is the representation learning. And, you know, it's a sort of like a linear function that actually that learns a projection from the multimodal features to the terrain type distributions. So that is the Z here.
So the demonstrations are X here, or?
No, there's no dimension. Well, no, X is the sensor data, like the LiDAR data, different features, like, you know, go back. So those are the X. So those are all different features from the observation, and those are the X. And we just concatenate them into a single vector. Okay. And we just use these features. It's just a classic, you know, you say like an object classification problem. So we generally use these features to classify the terrain types, and it becomes a multinomial distribution over a set of predefined terrains. And then the second part is, after we learn this, like this, you know, representation space like a Vx, so that's sort of like in the distribution space of the terrain types. We learn another projection from that hidden representation space into the robot actions. So the robot actions is Y. So that part is actually is also started from learning from demonstration, and then there's some self-supervised learning there. Okay,
I see.
And these two parts are not that new, but the novel thing is the sparsity not regularization terms. So those certainly are used, for example, to help us to squeeze out you know, noises from the sensor space, and can help us to unify, you know, the action space. Like, you know, we can just make the representation to be more representative and distinct from others. So those are the novelty. Yeah, I do not expand them, but you know, they actually solving this problem and designing this sparsity of regularizations. That's the main novelty for this work.
Okay.
Yeah, and it's highly efficient. That's the key. We can run this like 300 hertz. Yeah, for control loop. Yeah.
Excellent.
Sure.
I actually have a question related to this part. I think you showed that your method can take a shortcut compared to other methods, right?
Yeah, that's not this one. That's yeah. But go ahead. Yes.
Is the objective function itself is different, or your method does not get stuck in a local minima and other method gets stuck?
Well, I think that's the design question. So you know, like we generally use the previous methods. We actually do not change their implementation, and when you tell the robots to go into the tall grass, they just do not do that, because those policies are trained mainly for obstacle avoidance. And when they see this tall grass, although it's navigable, the robot goes into it, right? But the sensor data tells them, okay, this is the obstacle, and the robot should not go into that. Yeah, so that's the main problem. Yeah. And the other thing is they do not have this functionality. Like, nodes have the ability to collect the data on the fly and try to use that data to predict the next several steps. And so that they actually can explore on the fly about within this tall grass. And the other methods, after it's trained, they have a fixed policy that actually never explores during the execution phase, right? So that's another limitations of the previous methods. Yeah.
Thanks. Are there any questions?
Actually, exactly the same question.
Okay, great.
Another question.
Sure.
I have a question about the feature selection. So choosing the RGB in the light condition and using depths in the dark condition. So how do they choose or determine the weights of their sensory input?
So this work follows a similar mathematical foundation that's like a regularized optimization. And I mentioned about the design of the regularization terms. So these regularization terms generally will decide the weights. So you consider like feature selection, right? If some of the features, they are not that important. So this feature selection, these regularization terms will just make it to have a weight close to 0. And if they have one feature that is much better than the others, and they generally, through sparsity in terms, they actually can just increase the weight of that specific feature. And if there's a subset of features that worked collectively well together, then that sparsity term will enable that. Yeah, so that's generally the design of these regularization terms. Yeah.
Okay, thank you so much.
Yeah, sure.
I have a question about the collaborative things, the second part. So do you train every agent at the same time, like using the centralized training model, or can you train in a decentralized model, or?
Yeah, good question. So the collaborative scheduling, we actually, let me just go here. Collaborative scheduling, we did not train the control policies, but the other two have the control policies. But the other two, like the tightly coupled collaboration and also the adaptive coordinated navigation, they are homogeneous robots. When you have heterogeneous robots and when we want to do, the team level behavior generation and the individual robot generation with heterogeneous robots, that's actually not easy. We have a paradigm to train, to have this centralized training and decentralized execution. And in that phase, each robot have their own control policy. And this control policy for each specific robots can be pre-trained or it can be trained together, but it must satisfy certain conditions. For example, basically what we are doing is still follow the standard gradient-based methods. So if we can propagate the errors from the individual robots to the team level and then propagate it back, then they can use the same methods. And they can use this local controller together with the upper level team level policy generation. And if these two, if they have different methods, they are not based on gradient-based, solvers, then they cannot combine them together. Yeah, and if some of the controllers for a specific robot, like humanoid control, for example, they already have a controller, then we just treat that as a part of the system, and we are not going to further train that component. Yeah. Yeah, sure.
Any other questions? Okay, maybe it's time to wrap up. Thank you for a great presentation. And let's thank the speaker.
Thank you, everyone.